Hello everyone. Here is Weiqi Wang, grad candidate from Clemson University, and I work for Dr. Pozzolans graduate. Today we are going to present the topic feasibility of using high-alkali natural pozzolan and reclaimed fly ash as alternative cementitious materials, supplementary cementitious material in the concrete. Previously, the high-alkali SCMs are not recommended to be used in the concrete industry because the alkali content are believed to release into a concrete pore solution, which increase the challenging for controlling the alkali-silica reaction. But right now, due to the traditional SCM like fly ash are running out, and therefore the demand for the alternative SCM in the concrete industry has increased significantly, which provide us a motivation for our study. Also, there are other research bases for our work. First, there is no specification in the industry for limiting the threshold value of alkali content of SCMs. The primary standard ASTM C1567 does not give the value. Also, some previous literature review indicate that not all alkalis of SCM are readily available for release into a concrete pore solution. And here is the materials table we used for this study. And generally, the SCM contains over 3 to 4% alkali content are considered as high alkali SCMs. So in this study, we evaluated 6 natural pozzolan and 2 reclaimed fly ash. And the alkali content of this material at least 4.56%, so they are considered as high alkali SCMs. And here is the particle size distribution of the materials, which is measured by laser diffraction. Even though all these materials are SCMs, the significant difference of the median size among the materials indicate this material they are supposed to behave differently when they blend in the concrete. Then I'm going to show the alkali-silica reaction results, which is a primary concern for using this kind of materials. The ASR is a concrete durability problem that results from the deleterious reaction between alkali hydroxide in a concrete pore solution and the reactive forms of silica typically present in the aggregates. This reaction will result in a significant maintenance and reconstruction cost. The most effective way for mitigating the ASR is to use the SCMs. The mechanism of SCM can be summarized into 4 aspects. First is clinical dilution. The second is reduce the permeability of the concrete. The third one is consume calcium hydroxide. This process So the third way is consume calcium hydroxide. This process also referred as the Pozzolanic reaction, and the product of the Pozzolanic reaction are able to bind the alkali ions, which further lower the pH of the pore solution. And the 3 different methods we conducted in this study. First is ASTM C1567 AMBT. This method is the most time efficient. It only needs 14 days for finishing test. And the second method we use is ASTM C1293 CPT test. And the test needs at least 2 years for finishing, but it provides much more accurate than the ASTM C1567. The third method we use is AASHTO T380 MCPT. This method combines the advantage of the previous 2 methods. This has, compared to the first one, it provides much more accurate results. And compared to the second one, it's relative time efficient, which only needs 56 days and a maximum 84 days. Of course, different methods have different criteria for the evaluation. And here is a comparison result from different test methods with 20% SCMs replacement level. And first of all, different tests yield different results. In the ASTM C1567, all the material passed the test, and their expansion are lower than 0.1% at 14 days, but they all failed to pass in the 1293 at 2-year test. As for the AASHTO T380, majority of them passed the test, but still some of them failed to pass. Here, I want to make a point here. Even though some materials fail to pass at certain tests, does not mean they are not effective for mitigating the ASR, because if you compare to the control's value, all the materials significantly lower the ASR expansion. So if we change the reactive aggregate from this kind of reactive to a relative low reactive aggregate, their material they possibly effectively pass the test. So another thing I want to point out is MP6 and RFA1. MP6 has the highest amount of equivalent alkali content, but its performance was not the worst. The worst one is the RFA1. It has the highest expansion among all three different tests, but its alkali content is only 4.69%, which is the second lowest one. Therefore, based on the comparison for the two materials, a conclusion we can get is using the alkali content of SCMs to predict their ASR mitigation performance is not very comprehensive. And in the previous test, that 20% dosage level seems not sufficient for mitigating the ASR past the test. So therefore, we conducted some high replacement level tests. This is the MCPT test. We increased the replacement level from 20% to 30 and 40%. And obviously, increasing the replacement level really significantly lower the ASR expansion. We also did the same test in the 1293. Right now, the comparison has already lasted 18 months. The result has the same tendency with the previous MCPT, that high replacement level had relatively lower ASR expansion. Then we use a different Pozzolans reactivity evaluation method to explain the result in the ASR. We primarily use 5 different methods. The first one is to use the X-ray diffraction for quantify the crystallinity or the amorphous level of the SCM we used in this study. Generally, the more amorphous area, the more amorphous content of SCM, the more reactive of the SCMs. And then we use some classic method, ASTM C380 strength activity index, and a relative advanced method, ASTM C1567 isolate test conducted by the isothermal calorimetry. Servogravimetric analysis, TGA, were used to quantify the amount of calcium hydroxide in a cementitious matrix. And the inductively covered plasma spectroscopy was used to quantitate the amount of the alkali ions in the cementitious post solution. And this is the XRD pattern of the materials we used. And except the MP3 and MP1, rest of them are very amorphous. For the MP1 and MP3, lots of crystal peaks occur in this degree, the angle degree. And we do a simple linear regression between the SCM's amorphous level against the 84 days MCPT expansion, and there is non-correlation existing between two data sets. Here, I want to point out the MP3 data point. Even though the amorphous level here is very low for this material, it still indicates very good ASR mitigation performance. So we predict that some crystal phase of SCM still can engage in the chemical reaction. And here, the amorphous level was calculated based on the integrated surface area of XRD pattern, using the integrated surface area of the crystal peak against the total surface area. And here is a strength activity result. Except the MP1 and IF1 7-day result, rest of the sample are satisfy requirements that in the ASTM C1618 reach 75% of the control. And this is a ASTM C1897 isolate test results. All the materials have at least around 300 or over the 300 joule per grams. So they are all considered as very high Pozzolans reactive materials. We also do a simple linear regression between the R3 test against the ASR results, and not significant correlation between two data sets. And here we want to point out this red point, which represents the IFA1 data point. In the previous ASR expansion results, the IF1 has the highest expansion among all the materials. Even in the strength activity results, as at 7 days, it failed to pass. But in R3 test, it released the highest heat. It released the highest amount of heat. So, and we believe it's primarily caused by the test environment, because in the R3 test, the test temperature is relatively high, 40 degrees Celsius, and the pH of the environment is extremely high alkaline. So we believe that this kind of environment may increase the reactivity of these materials. Then we run, this is a TGA result, and we calculate the amount of calcium hydroxide of the paste based on the weight loss between 400 to 500 degrees Celsius. Consider dilution impact of the SCM, because all sample represent 20% SCM, so the calcium content was compared to the 80% of control. And here at 7 days, all the samples had higher amount of the relative calcium contents than the control, and we believe it's primarily caused by the failure effect of the SCMs, which provide more nuclear sites for the cement to have more high degree of hydration. And with time going by, the amount of calcium hydroxide decreased. And we did a correlation between the TGA and the CPT. They indicate very good correlation, especially the MCPT method, the AASHTO T380. Compared to the CPT, the correlation seems not very good, and R-square value is only have 0.67, and we think it's mostly caused by the sample age difference, because CPT tests all expansion the sample age is 2 years, but the oldest sample we measure in a TGA study is only 56 days. And these are the alkali ions concentration of the post solution. And the alkali ions include the potassium and the sodium. And here we have two replacement level, that is 20 and 30%, which shown by the blue and the yellow color respectively. And the solid field and the pattern field are represent for the 28 days and 84 days represent respectively. And in this study, we also consider the dilution effect, and the blue dashed line, yellow dashed line indicate the threshold line for the control after calculated by the dilution impact. And except for only IF1 exceeds the threshold limit line, and the rest of group are lower than their corresponding limit line. And here I think some maybe notice that at some sample for 84 days they have a higher alkali concentration than their 28 days. But here it's very hard to explain, because there is a dynamic balance in the cement matrix. On one hand, due to the Pozzolanic reaction, they can combine the alkali ions, but on the other hand, it's possibly release more alkali ions from the material itself into a post solution. So till now, I cannot explain the real mechanism of the materials, but from a big picture, all the 30% replacement level has the low alkali concentration compared to their 20% replacement level. And we also did some linear regression between the alkali ions against ASR results. It seems to have a good correlation, because R-square is around 0.8, but we noticed that if we remove the data point of the control, the highest 3 points, there is non-correlation exists in this figure. But we still go back to a point we get from the previous figure, that using this high alkali SCM still effectively to lower the alkali concentration in the post solution. Then we also do some analysis for a durability perspective. First, we select 5 materials for running the dry shrinkage test, and based on the results, all the materials has no no significant impact on the dry shrinkage. The results are very consistent with some literature review that the cooperating with SCMs have no significant impact on the dry shrinkage. And we also run some surface resistance tests according to the ASTM C1293. It's very apparent that SCM lower the surface expansion. The cement we use in this study is type 1 and 2, and based on the Bogle equation calculation, the amount of the C380 is about 5%. So it's relatively low value. So maybe it could be the answer for explaining why the difference between the control and the SCMs appears at a very late age, that's 35 weeks. And we done some permeability test for the ASTM C1293 ICPT test. Except the RFE1 rest material are still effective to control the amount of charged pastel concrete lower than 100, lower than 1,000, which I consider a very low zone. And at last, we conducted some electro bulk resistivity. The high resistivity means that low conductivity. Low conductivity means less chemical reactions. And in these figures, that the black line indicates very differently from the rest of test materials. The first measurement is at 3 days at that corner. The control has the highest resistivity value compared to the rest of group, but it's entering in the plain tune phase at a very early age, and then it's increased very stable. But yeah, the line change is very stable, has no significant difference. But for the rest of SCM group, even right now it's already 4 months, it's over 110 days. This still indicates a very strong tendency for increasing, especially the yellow line and the MP4. And we do some correlation between the bulk resistivity and ICPT because those two methods are considered the method for evaluating the permeability of the concrete. The result indicates a very good correlation. And here is my conclusion for this study. First, the different ASR test method yield different different results. Per ASTM C1567, all the material passed tests, but they all failed to pass the 1293. Also, using the amount of alkali content of SCM to predict their ASR mitigation performance is not comprehensive. And the result indicates that at higher replacement level, the high alkali SCMs are performing much more effectively in mitigating the ASR. And the ASR expansion has a very good correlation with the TG result, but does not correlate very well against the R3 test and amorphous level. Strength activity index are not persuasive to represent the pozzolanic reactivity of the SCMs. And the post-solution chemistry in this system supports results from the ASI experimental test. And all SCM effectively lower the alkali concentration in the post-solution. And higher SCM repeat level further decrease the concentration. And results obtained from the RCPT and the bulk resistivity indicate that cooperating the high alkali SCM in the concrete makes the concrete matrix denser compared to a control, and this material also increases the surface resistability of the concrete. And based on the findings from in this study, high alkali SCMs can have a solid potential to be an alternative SCM for the concrete industry. We thank you for support of National Natural Pozzolan Association and its member company for providing us the material for this study. So do you have any questions?